That we're connected good?
We'll get it one of these days. They'll get used to it. I think the Robbie group will join us.
We hear you now.
We hear you now? Okay,
Yeah.
good. We're ready to get the show on the road. Purpose today, or the main thing I'm going to do is I'm going to finish off some of these mathematical issues. Make sure that we know all the various mathematical skills we want, and then maybe talk a little bit about the Michelson-Morley interferometry experiment. For the people here, we will do the Michelson-Morley interferometry experiment next week. But we will not prove that the ether doesn't exist. We will be using the interferometer as a way to measure the wavelength of a laser. And so that will be your laboratory experiment. And you'll have to learn all the difficulties that come with making sure that you get an interference pattern by a coherent laser. Vibration problems, alignment problems, and so forth. But it turns out interferometry is a very powerful technique. You can do atomic interferometry to actually look at the interference patterns of atoms as a way to do a lot of advanced physics.
Awesome.
First thing I want to do is I gave you guys a problem to finish up out of problem number 4, and I want to look at problem number 4 for a couple of reasons, partly because it actually leads to the famous equation E equals mc squared. And so in some of the later notes in one of the later sections, we'll come back to it, but I just want to look at it from the, although that's a very interesting way of looking at our shirt. Is that important? Let's see. So I want to look at that. I asked you to prove that you get the kinetic energy formula out of this particular equation from last time. And so turns out that's the total energy. I'll show you in a second. That's what's called the rest energy. What I wanted you to prove was that that's actually the kinetic energy, and that that's what you get for low speeds, which is what you had back in Physics 1. You may remember, those who had me in Physics 1 know that I put there specifically that kinetic energy formula, 1/2 mv squared, is not the definition of kinetic energy. Kinetic energy's definition, the only correct definition, is the energy an object has due to its motion. One of the reasons I emphasized that, I told you, was that formula was based on some assumptions, one of which is the mass was constant. It's derived out of the work energy theorem based on that. And we're going to find out in relativity mass is not constant. Mass changes with velocity. And that's, in fact, where this whole discussion comes from. So I want to go piddle with that, and let's at least see if you came up with the correct way to do this. We had to use a binomial expansion on the bottom part. So let's first look at this guy. So that can be written as 1 plus a minus b squared over c squared to the minus 1/2. So if you write it like that, then there's your n for the binomial expansion, and there's your x. So that means this has to be approximately 1 plus a minus 1/2 times minus b squared over c squared, using the binomial expansion. So we had 1 over the square root of 1 minus b squared over c squared is approximately 1. I have a minus, and a minus makes a plus. When v is much, much less than the speed of light. So I take that, and I multiply it by m naught c squared here to get the first term, and then I'm going to subtract m naught b squared. So if I do this, m naught c squared over the square root of 1 minus b squared over c squared minus m naught c squared is approximately m naught c squared 1 plus 1/2 v squared over c squared minus m naught c squared. So I have m naught c squared, that's this times that term. And then you should have found plus m naught c squared times 1/2 v squared over c squared. Those canceled. And then minus m naught c squared. Well, that cancels this. So 1/2 m naught v squared. And that is the kinetic energy for a slow-moving object. That's just an application of the binomial expansion, yeah.
How much smaller than C does B have to be?
Good question. So the statement is, you know, how much smaller do you have to be in order for you to consider this approximation, just two terms, rather than an infinite number of terms, be satisfactory? Well, the answer is, how much error do you want? In practice, if B is less than about 1/10 of the speed of light, we're talking about way less than 1% error. Now, if you're going to build a device, let's say for an engineering application, and it requires you to be in 1 part in 10 to the 9, then you're going to have to look where this direction is to within 1 part in 10 to the 9. And so then this thing is going to have to be much, 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 much less. All right, so you can do that by simply looking at the first two terms and then look at the next term. And see how much the next term corrects. So if you take the ratio of the third term to the second term, you're finding out how much leaving off, because each term after that's even smaller. You're going to find out roughly about how much your error is. So you just compare the two terms. Rule of thumb for this class, if it's within 1/10 of the speed of light, you must apply relativity. So when we say much less for us, we mean the speed is less than 0.1 c. If it says it's half the speed of light, you better include relativity. If it says it's 0.001 the speed of light, then you can ignore relativity and use classical physics. That'll be important when we start dealing with atomic physics, because later on we're going to have photons. Let me change myself back on the instructor. We're going to have photons come in and they're going to hit an atom, for instance, or an electron in the atom, and the question is going to be, do we need to do relativity to calculate, for instance, the energy of the speed of the electrons that come off? And the answer is going to be, it's going to depend on the energies of the things involved. Sometimes the answer will be yes, and sometimes the answer will be no. And if you apply classical physics, and in fact the energy was enough to make the electron relativistic, you'll get the problem wrong. So the rule of thumb is 10 to the speed of light, okay, you must use relativity. And that's why we do relativity first in this class. Now I want to go back just before we leave it, just because part of the reason you do a physics problem is not just to get an answer. You want to understand and try to figure out what it's trying to tell you. So, see what a physicist would think about this problem. Units. Units are an important thing. Units tell us something. If something has units, then it probably means it's physically the same type of quantity. So the result of this is an energy. And it's an energy of motion. So that means these other terms must be energies too. Now if you look at this term here, if V was 0, if you weren't moving, if V was 0, then this would be m naught c squared. So it would be an energy exactly the same as that, but it'd be an energy that you would have without moving. And then if you are moving, the difference between this term and the energy you have if you didn't move is the energy of motion. So let's just think about that. The difference is the energy you have due to moving. The term there is what you would get if you put V equals 0. So that must be the energy you have without moving. So I've got minus the energy at rest is equal to K the energy of moving. Well, if you've got the energy you moved, you subtract what you took for energy of, if you have the energy of motion away, let's move this over, then you'd have the energy of motion plus the energy at rest. That would be what type of energy? That'd be all the energy. So that must mean this is the total energy. So just by thinking about the units, you can figure out what the heck an equation is trying to tell you. If you're a professional physicist and you're trying to find a law, it's not written in a book yet. You're finding it before anybody else ever found it. That means you've got to be able to look at math and figure out what it's trying to tell you from an experiment without anybody having told it to you before. This is how you play the game. You do thinking, and you ask about units. And you look to see how the equation changes. And it provides the guidepost by which you figure out how to do your job. All right? That's how you become famous. That's how you develop your professional identity. So, Einstein, when he was playing with this, that's rest. Hey, at low speeds, that gives me kinetic. So, if that's energy of motion and this is energy of rest, this thing must be the total energy. This total energy must be something c squared. This is the mass at rest. Hell, you can think of this as like the mass, m, and you get equals mc squared, and that's where the famous equation comes from. So you can either think of kinetic energy as energy of motion, or you can think that what happens when you move is it changes your mass. Now, Einstein didn't like this kind of interpretation in a way for the following reason, that how would you weigh it? It doesn't make sense to talk about you have a different weight. And since the mass depends on the speed and the speed depends on your frame of reference, then it depends upon, your mass depends on your frame of reference, meaning you wouldn't have anything intrinsic to you. So he preferred to think of the mass as an intrinsic thing and only think rest mass had a meaning. The idea that there's something else, he liked to take this term in front and put a gamma and say there was a factor there. And that factor actually caused the change in your mass, was a statement that it actually was causing you to have this energy of motion, and that was stored. The fact that the energy of motion, your mass, if you want, changes with your frame is not surprising, because if you're on the ball and the ball's flying, the ball's at rest, it has no kinetic energy. But if you're looking from over here and you see a ball going by, the ball then has a velocity in your frame, it has kinetic energy. So energy is frame dependent. And you have to have a frame in order to determine the energy. These are all various things that we're going to be dealing with in these next couple of chapters that you have to read very carefully. Right? You have to make sure you understand the terminology. The mathematics of the binomial is going to be an important thing to be able to have in your toolbox to work homework problems. So make sure you master the math. In the process of doing the math, try to pick up some physics too. You only have so many hours in the day. If you can learn two things with one problem, then you've done twice as much homework than if you did the problem and you only got one thing out of it. Thinking about a problem when you get the answer is the most important part of the homework problem. If all you do is get an answer and turn it in, you did not get much education. And you'll have to do a whole lot more work to get the same education as somebody else. Get the problem done, and then sit and think about what the problem tells you. That's where you really get the education. All right? So don't rush through the problems and not think about your results. Your results is where you get the deep learning. So think long and hard about it. Other things that you need to be able to do. You need to be able to do a Taylor series expansion. They're very important. So I gave you in that set of notes a set of problems, wrong one, number 5. It asks you to do a Taylor series expansion. Hopefully you did these in math before. I want to look at them because they connect the complex plane and your trigonometry, and it's a good chance to make sure that you are an expert in trig by now. So let's look at the cosine of theta, because there's a lot of things you can think about it. If you expand this one, we want to expand this function so that we write the cosine of theta is equal to some constant, A naught, plus some new constant, A1 times theta, plus some new constant, A2 theta squared, plus some new constant, A to 3 theta cubed, and so forth. And the problem is to find those constants. And the way to do that is the Taylor series expansion. Why would we like to do that? If theta is small, then we are converting a trig function into a polynomial that's easier to integrate, it's easier to differentiate, and it's easier to graph. So it can make things simple, but only if this is small. Again, it's an approximation technique to work problems because the equations can be so difficult they have no solution methods in general. All you can do is work them for special cases. So one of the ways that we do that is to do this type of expansion. In the notes, I said to find a particular constant, the nth constant. You take 1 over n factorial and take the nth derivative of the function. And evaluate it for whatever that function's particular location. In our case, it'll be for theta equals 0. So let me show you how to do at least a couple or 3 or 4 of these and see if you got them right. So let's take A0. A0 would be 1 over 0 factorial plus the 0th derivative, theta to the 0, of the cosine function when theta is equal to 0. What's 1 over 0 factorial? 1. Okay. What's the 0th derivative of a function? It's the function. So the 0th derivative is just the function itself, and I want to evaluate the cosine when the cosine has theta of 0. So it's 1 times the cosine of 0. What's the cosine of 0?
1.
So that coefficient is 1. Whoopee. Well, first of all, it tells you how they get the fact that the cosine of theta for small angles is approximately 1. That's where that formula comes from. But it's an error because there are higher terms that need to be added. All right, so it's an approximation. Something else. Look at it graphically. So if I was to graph this thing, to the least best of my ability, there's my cosine. And there's 1. And you ask me what's the answer at, say, this location right here, or even right here. My first best guess is it's 1. Now, you can tell that if you're over here or here, it's not 1. What could you say about it?
It's a little less than 1.
It's a little less than 1. So the next term needs to subtract from that. And it needs to subtract about that much. And oh, by the way, whether you go plus or negative, it needs to subtract. So whether you put plus theta or negative theta, you need to subtract. Well, that means it can't fit a straight line. Because if you fit it a straight line, it would go like that. So over here would have a negative, and over here would have a plus. That term's got to be 0. What you could fit is a parabola with a negative coefficient in front of it. In other words, you could have that term with this be negative, and it would subtract a little bit on both sides. And that is, in fact, the next best fit to this graph. Because you always have to produce a negative amount, all the odd terms will go to 0. All the even terms will reside. This is why it's an even function. In fact, how it comes about to be known to an even function. So if something's an even function in a Taylor series expansion, only the x's or thetas, whatever the variable is, to the even powers will remain. If it's an odd, only the odd ones will remain. And any function can always be written in terms of an even plus an odd function. Any function. By the way, there's a statement in physics that says that. It doesn't talk about even. We talk about parity of wave functions in quantum mechanics and modern physics. All energy levels in an atom are either even parity or they are odd parity. They will either be even functions or they will be odd functions. That's a fact. It's one of the fundamental things we want to measure in doing physics, is parity conserved. So these ideas of even and odd, they come back throughout this course. We don't talk about them the way math people do. So it's a good chance not only to be able to do this, but to go back and think about what this is trying to tell you in terms of physics. Let me go ahead and get a couple more terms here because I want to use it for something else. But that's the graphical. So when you see that, make sure you can see this. When you see this, make sure you can see that. If you can't, you haven't thought enough about it. Let me prove that A1 is 0. I get 1 over 1 factorial, and I get the derivative with respect to theta of the cosine function. For theta equals 0. Well, 1 over 1 factorial is 1. What's the derivative of the cosine? Somebody preview.
Negative sine theta.
Negative sine. Very good. So I got minus sine. What's the sine of 0 degrees? 0. So sure enough, there's no term. If you take the second one, you get 1 over 2 factorial now. But you'll now have the second derivative of the cosine function, which is 1 over 2, and the derivative of whatever the first derivative was here. So it's the derivative of this, which you just told me was minus sine. And what's the derivative of sine function, anybody? Cosine. So I now have minus 1/2 cosine of theta at 0. That's minus 1/2. So you want a little better function? The cosine of theta is approximately 1 minus 1/2 theta squared. That's a little better approximation. And I can keep adding terms. By the way, that is how your calculator calculates the cosine function. It does not know about triangles. It does not know about geometry. But it knows damn sure how to add and multiply. So a calculator, when you ask it to calculate the cosine of 37 degrees, the first thing it does is it knows it can't do degrees. Degrees are not an appropriate way to do an expansion because each one of these terms has to be unitless. If this had a unit of a meter, then that would have a unit of a meter squared. This would have a unit of a meter cubed, and then a meter to the fourth, and you can't do that. So these have to be unitless. Degrees are not unitless quantities. Theta is a unitless quantity because it's defined in terms of the arc length. For that's S and that's theta, and that's the radius. Theta is S over R. That's its definition. So the length here was in meters, the radius was in meters, the meters cancel. The radian is a unitless quantity, and so it can be used in such expansions. When you do trig or you do calculus, anytime you're not just pressing the calculator button, you probably want to be careful and be in radians, because if you're doing calculus in degrees, which means you're summing, say, for instance, do an integration, an area in the curve, it can be wrong because it's not a unitless quantity. It can't be done like that. Now, if you have experience, you know when it'll be wrong and when it won't. The answer is probably better to avoid the bear trap and just put them in radians to start with. Your calculator does that. As soon as you put the degree in, it converts it internally into radians, and then it does the math. That's what it does. All right? Something else that's interesting, if you were to continue doing this, you would find things like this. This would be 1 over 4 factorial theta to the 4th minus 1 over 6 factorial theta to the 6th, 1 over 8 factorial theta to the 8th. Nothing wrong about that, but notice how the signs are they're flipping. You can get rid of the flipping sign if you take into account something else, the complex number I. I squared is minus 1. I to the 4th is plus 1. I to the 6th is minus 1. So on and so forth. So I could rewrite this way. Cosine of theta is I to the 0, theta to the 0, 0 factorial. That's 1. That's a weird way to write 1, but that's 1. I to the 0 is 1, theta raised to the 0 is 1, 0 factorial is 1. Plus I squared, theta squared, 2 factorial. I squared will give me the minus sign. There's the theta squared. There's 2 factorial, which is 2. I to the 4th, theta to the 4th, 4 factorial. I to the 6th, theta to the 6th, 6 factorial, and so forth. So in other words, this is cosine theta. It's I theta to the 2n over 2n factorial, summed from n equals 0 to infinity. I can write it very compact. Why would I want to do that? Because I want to use this to develop complex numbers in just a minute. So if this is 0, then that's that term. If this is 1, then that turns out to be that term. If n is 2, it turns out to be that term, and so forth. Notice that the I has gone in with the theta to make an argument. So it's like the x. And the 2, the only purpose of the 2 is so that I skip all the odd terms. You'll see this a lot in math and in other physics classes. I would put it to memory, or at least something where you quickly know it, so that if you see something like this, could be anything, could be some weird I-7 or I-12 or whatever, that you immediately say, oh, if I see something that where this is 12, like this is 12, and this is 12 squared over 2, and this is 12 to the 4th over 4 factorial, I immediately say, oh, you mean the sine of 12? I mean the cosine of 12? That's how I add up those infinite number of terms? If you're not used to seeing it like that, you will not think of it. You'll just have this infinite number of terms. You won't be able to solve problems. Okay? So, put this one to memory. Play with it. Think about it. There's not a lot of them that show up in physics, but those that do, you need to know. You get a lot more of this in a class called Math Methods, for those of you who are getting your chance to bite your teeth on it. Yeah?
Shouldn't there be parentheses around the 2n in the denominator?
Shouldn't I have what?
Parentheses around the 2n in the denominator.
Yeah, you're right. He says, shouldn't I really do this? And that's correct. I thought I did. I didn't say it. You're correct. I don't mean n factorial multiplied by 2. I mean the 2n. You're absolutely correct. If I don't do that, then I'm going to get it wrong. Now, you can do the same thing with the sine function. You can start writing out its terms. And hopefully you get it. So I'm going to save myself some time. I'm not going to actually work these guys out. I'm just going to write it because I want to jump to something for the next problem. So I'm assuming that if you can go through this, and if you can't, you got problems, give me a call me up. But you should be able to prove that sine theta is equal to 1 minus theta cubed over 3 factorial, theta to the 5 over 5 factorial, theta 7 over 7 factorial, so forth. You get an alternating signs, and that you get only the odd powers. By the way, you could write this one as theta to the 1 over 1 factorial. Now, I just got through saying I could get rid of these stupid minus signs by doing the I squared trick. So I'm going to do the same thing. Let's see, this one, there's no problem. I'll just leave it alone. This one, I need to get rid of the minus, so I need a plus I squared. That one I need a plus, so I'll put I to the 4th. This one I need a minus, so I'll put an I to the 6th. And I got rid of the minus signs, but what looks wrong here is that the i's don't match up. For instance, if you want to, you can put this as I to the 0. The i's do not match up with the thetas. So I can't put them inside of parentheses like I do there. What am I missing? How many i's are missing in each term? Anybody? 1. So, okay, so what you do to the left-hand side, you can do to the right-hand side. So if I didn't write sign, if I was to write this as I sign, then that would raise this to the 1st, this to the 3rd, this to the 5th, this to the 7th. So if I write I sign, I theta to the 1st over 1 factorial, I theta to the 3rd over 3 factorial, I theta to the 5th over 5 factorial, I theta to the 7th over 7 factorial, and so forth. And now it looks an awful lot like the cosine. The sine has all the odd ones. The cosine has all the even ones. That's kind of interesting. Well, that's what brings up the question that I had on number 6. Number 6 said the following. Use the Taylor, whoops, let me move it up a little bit. It said use the Taylor series expansion to prove that e to the I theta is cosine theta plus I sine theta. And figure out geometrically what the hell does e to the I theta, a complex exponential, look like. This is known as the Euler form of a complex number from trig class. Well, it's all here. There's a bunch of terms there. And I had the cosine right above. So what I want to do is I want to add both of those and see what they're at. And I need to know one other fact. And the other fact that I need to know is the following. E to the x is x to the 0 over 0 factorial, x to the 1 over 1 factorial, x to the square over 2 factorial, x cubed over 3 factorial, so forth. Know this. You should have known it already in your math classes, but if you haven't, put it to memory. Again, a lot of physics in this. These terms, whatever's up here in this exponent, in an exponential, must be unitless. We did that in Physics 1. You didn't have me for Physics 1, and maybe you didn't. Go back and look at the book. There's a book called Use Math by Clifford Schwartz. from the American Institute of Physics. Go back and make sure that you know things like this that were in your math classes. You know, they get so hung up on trying to figure out if Johnny's going to be able to solve algebra that they're not really too worried about the people who do well picking up all the things they need. These are important things. The fact that this x has to be unitless is what tells us things like when we look at time constants, that they have to be time constants. And when we look at half-lives, they have to be half-lives. That's how we get all that stuff. It also tells us something else. Well, look at these. They're all plus. So if x was a real number, each one of these terms, if this is greater than 1, is going to get bigger. And this number is going to blow up. Yeah, that's what happens. This number, x gets very large. This thing blows up. Something else that it does. If it's a negative number, then you have a number, and then this one's going to end up being negative, and then this is going to be positive, and this is going to be negative. It starts binding and going down. What would happen if that was not x, but was I theta? If this was I theta, then this would be I theta to the 0 over 0 factorial, I theta to the 1 over 1 factorial, I theta squared over 2 factorial, I theta cubed over 3 factorial, I theta 4 over 4 factorial, and so forth. Now if you look at that term, hey, they're right there. And this term, and this term, those are the even terms of the cosine. So if you break this into two parts, you put all the even powers together, that's the cosine. And then you add these odd terms, that's I sine. And what I said is cosine theta plus I sine. That's where that comes from. That's how we know that. All right? It comes right from the expansion of the Taylor series. Now, let's play one more thing about it. So that's how I proved that. If you were to write this thing, let me now graph this. If you were to take an arrow like this, that arrow was 1, and this was the real part, and this was the imaginary part, then that thing looks like something we call a vector. And it has parts. There's a real part. There's an angle theta here. There's the real part. It's the length of the arrow, and you're looking for the adjacent side. And an adjacent side starts with the letter A. When you want to find an adjacent side of a vector, because it starts with the letter A, you use the trig function that's closest to the letter A, which is C, cosine. So 1 times the cosine gives you this side. When you're looking for the opposite side of the vector, starts with the letter O, then you use the trig function that's closest to O, which is sine. This side over here is found with the sine function. But that sine doesn't point along the real, it points along the imaginary. So we put the I in there to tell you that it's going in that direction, just like the J hat. So what's this? Well, it's that vector plus that vector. So it's that. So an arrow whose length is 1 is that. It has a length of 1 and it has a direction of theta. If you want to make a complex number have a different length, multiply that by a different number, like 7. Just stretch the arrow 7 times. Everything about trig and complex numbers you ever want to know are contained in that arrow. All the trig identities. Everything you want to know is there in that. Let me show you. Let's say that you wanted to know, for instance, you had something like cosine of 90 minus theta. And I wanted to know what that was. Okay, let's see. That angle right there is 90 minus theta. And the cosine function says find the adjacent side. So that's that. Okay. So that's cosine of 90 minus theta. Well, heck, that's the same as that length. So that means that's equal to the sine of theta. That's the trig identity. Everything you want to know is there. All you have to do is know how to coax it out of it. And where does it come from? Does it really come from geometry? No, it really comes from these sums. So the Taylor series expansion. So this expansion is incredibly powerful for dealing with any problem that involves vectors or trig. What involves vectors and trig? All of physics. So, not just for this course, for E&M, for Nuke, for whatever course you've got to take in the future. Go back and make sure you master these type of math skills. Make sure that you know them really well. It will save you hundreds of hours of homework time. And you don't have that much extra time. We give you lots of homework. All right? Teachers give you plenty of stuff, and every year the homework problems get harder. If you don't have good math skills, it's going to take you a lot longer to do them. I had a set of complex number problems that I asked you to work. And the reason we care about complex numbers is when we get to wave functions in quantum mechanics with probability, they're going to be complex numbers. And they're going to be complex mathematical functions. So if your complex numbers are not good, you'll struggle in those sections. We're not going to do that for about 2 months, but we'll still do that. So make sure that you get and work on them. There are a series of these that I gave you, and I gave you some straight numbers. And hopefully you can work through them. I'm not going to be so much work on any individual numerical problem. I just want to look on some more properties of these guys. But make sure you go through all of these, and if you have any questions, whether or not you got any right, send me an email, and I'll be glad to give you the answer to them, okay? Let me give you, say, a problem that was like this. And then you're asked its conjugate. Let's draw that. So, got some length A, and that's the complex number, so that's Z. That's theta. And if you were to draw the conjugate of that guy, let's draw him in a different color. How about red? Don't have red. You'd have the same angle in the negative direction, because that's a minus there. That would be Z star. Well, the thing you probably learned back in college algebra was they have the same real part. Well, of course they have the same real part. You can see that right here. There's the real part. So it's the same. But their y parts, their imaginary parts, differ by a sign. That's just Cartesian vectors. What would happen if you added Z and Z star? Well, you do vector addition. Come over here and you'd do like that. So you'd go up and then you'd come down, and when you were done, what would be the imaginary part of the answer? 0. Okay. And how would the real part compare to just the first vector?
Be double pi.
Huh?
Twice its magnitude.
Be twice its magnitude. Now, let's, for instance, assume that we made A 1. then this would be equal to that part, cosine theta, and then again. That would be e to the I theta plus e to the minus I theta. So then cosine theta is e to the I theta plus e to the minus I theta over 2. That's where that formula comes from. It's all in the arrows. Anything you ever want to know. Sine theta. E to the I theta minus e to the minus I theta over 2I. I'll let you prove that one. In this case, you don't add them, you subtract them. And they end up along this axis. Twice the imaginary part, and it points along I. Everything you want to know about trig, everything you want to know is contained in the arrow diagrams. Another really neat fact about these guys. These exponentials, they have a really nice property. When you take their derivative, you get them back. And the only thing you get down is a number in front of them. So it converts calculus problems to algebra problems. If you have a second derivative, it becomes a second order polynomial, and you use the quadratic formula to work it. This is known as the phasor transform. These guys are not going away. I don't care if you're an electrical engineer, acoustic engineer, nuclear physicist, solid state, I don't care what you are. This is the math by which we solve problems. So we'll be using it throughout the semester. I'm going to assume that you know it by now. If you don't master it, it will pay you many, 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 many big dividends. For one thing, you're just going to have a really hard time reading textbooks if you don't know your math. So, for instance, pull one of the chapters in here. Wave functions, like find one here for hydrogen. These guys have complex exponentials to them. There's the hydrogen wave functions. So you can see the complex exponentials and such showing up. You've got real exponentials, you have cosines, you have complex exponentials. So you're going to need to be able to handle complex numbers. Make sure you start practicing on them. You got quite a few chapters before you have to deal with them, but we're going to hit them again. Make sure you practice them. Binomial expansions we're going to hit right off the bat because they're in relativity. We're going to deal with the question of how do you compare relativistic speeds to classical speeds, and that's a small approximation. Complex numbers are going to be essential to handling anything that deals with the atom. And the reason is because these angles get into it because it's a spherical geometry. It occurs in all spherical problems. So you're going to need complex numbers. So practice them. If you have trouble, let me know, and we'll work on it. Questions about math? All good? What time are we at? So we're at the end of the semester. Okay, so we're at the end. Next time, go ahead and make sure that you watch the video on the Michelson-Morley. We'll start out with the simplest type problems, which is look at length and time dilation and complete contraction. And then from then, we'll do more difficult problems. First thing is can you measure a length of something? That thing, you know, is just sitting there like putting a ruler up against a desk. The harder problem is, what if you had two particles and one hits one detector over here and another hits another detector over there, and the two detectors are separated in space, and they're also separated maybe in time, and you have to do the full Lorentz contraction or transformation. Those are the more difficult problems. We'll start with just the length and time dilation, the simple ones, and then we'll move on. So make sure you watch video 41 on Mechanical Universe, and go ahead and watch video 42 and read the notes, and we'll pick it up next time. All right? All right, see you then.